Hello there, right, we're back for matrices lesson 6, I think. Here is a little teaser or a starter question that goes over things that we talked about last lesson, the eigenvalues and the eigenvectors. There's not much different in today's lesson, just more practice of it. Well, let's have a look at this one. So you're going to pause in a minute and have a go, but if you need a few hints, it says given this thing is an eigenvector of the matrix A, find the eigenvalue of A corresponding to that thing. So if you remember what we were talking about, we had, because it's all linked in with what you did in variant lines, invariant point stuff, but here's your matrix A. If you do this to an eigenvector, then it should stay the same or become multiplied by some constant, and that constant's called the eigenvalue afterwards. So what you have to do, you have to put your A and your V in and equal to lambda V, and then solve some equations. If you solve the bottom one, you'll get all numbers. If you go with 1, 1, 1 against this 0, 1, minus 1, then you'll find lambda quite easily. The P and Q you can also find from this bit of thing. It'll help you in there to find that with that. And then it says you're given an image, this thing, when transformed by that. Oh, sorry, when transformed by A, it's this. So you'll do here, you'll do A, and then that vector L, M, N, and equal it to 10 minus 4, 3. And you'll get 3 equations, 3 unknowns. Your calculator's good at that, so don't waste your time. Let your calculator have a play and see how you go. Right, let's pause the video then and have a go at those questions for me, please. Okay, unpaused. Here come the answers. And the bit it's hiding says gives. I'll write it here because you can't see it. 2, 1 and 0. So that's your L, M and N. Fantastic. Right. Let's look at what lesson 6 brings. It brings more practice in finding eigenvalues and eigenvectors by 2b2s and 3b3s. We've got to have a knowledge of a special property of the lead diagonal. Ooh. To be able to attempt all eigenvectors able to attempt to find all eigenvectors for repeated eigenvalues. That's when you get the same eigenvalue more than once. And then we've got to understand that when eigenvalues and eigenvectors indicate a transformation of a sphere, not sphere, shear, shear. Right. Reminder useful notes. Recall the steps for finding eigenvalues and eigenvectors are as follows. We first form that thing. What is it called? See if you remember. I'm going to spell it wrong. Yes, the characteristic equation. That comes from rearranging, go off you, mv equals lambda v. Rearrange that and you get that. And if you remember, it can't be an inverse. That's why the determinant has to be 0 when you bring him over. If you remember all that business, bringing him over, minus lambda. Then you pull out v as a vector, so you need to put an I in there, equals 0. If you remember, that thing can't be inverse. You can't have an inverse for that because v is not allowed to be 0. And it ended up being 0 if it did have an inverse. So if it doesn't have an inverse, that means determinant is 0. So we just solve that characteristic equation. So solve the equation to find the that lambda value, which is the eigenvalue. For each eigenvalue, find the corresponding eigenvector by solving that. Remember we did that last time. When you find an eigenvector for a 3×3, you are dealing with 3 simultaneous equations which have an infinite number of solutions. What you do if this is the case, you just take one of the values x, y, and z to be a value. Let's pick 1. And then find the other values for corresponding components. If you end up with any fractions, whoa, boo, we don't like fractions. If you end up with any fractions, just multiply the whole eigenvector by a constant, get rid of them. They won't in the exam allow you to leave fractions in your answers for eigenvectors. Remember that. Number 2, the lead diagonal. We mentioned that in the aims. Of a square matrix runs from the top left to the bottom right element, so the first to the last. The sum of the lead diagonal refers to sometimes as the trace, I think. Trace, yeah, trace. Is the sum, wow, it is the sum of the eigenvalues, whoa, magic, which provides a very useful way of checking your answers. If you found 2 eigenvalues, you can find the third by adding up the lead diagonal and taking the 2 away you found. Often very useful, that one. If an eigenvalue is repeated, is a repeated solution of the characteristic equation with multiplicity m, then there can be up to m eigenvectors associated with the eigenvalue. It is therefore possible for an n by n matrix to have fewer than n eigenvectors. If this is the case, then it is said it is usually associated, here we go. If this is the case, and it is usually associated with the geometric transformation of a, got it, sphere. So I mean, if it's got repeated roots and you can only find one solution to the repeated lambda, then it might be a transformation of a sphere, not sphere, not right talking about shear. You know what a shear is? It's like when you get a square and then it gets shifted along. It looks more like a part of it's shifted, but part of it's not. I'm doing bad diagrams. Well, it's a shear. Look it up. Example. Find the eigenvalues corresponding eigenvectors for this matrix. So first solve the characteristic equation. You've done a bit for me, good. So you have your A minus lambda I, which ends up with just taking lambdas off the diagonals. And then use the top row to expand it. Not supposed to have done anymore. No, so we're going to have to give a go. So we've got 4, take lambda. And then a big whirly bracket. What would happen there? Will it be 4, take lambda, 4, take lambda, minus 1, wouldn't it? And this one, minus 1, I'm not bothered with that, but put a big bracket. 1 times, so 4 times that, take away 1. And this one, plus, and this one's a 1. So it's 1 take 4 take lambda. Right, can we make that look any prettier? Well, I think I'm going to get some nasty multiplying out here. Yeah, not nice. Okay, so we end up with 4. You like 4 take lambda, we've got them 3 times, haven't we? So it's to the power 3. And then we've got minus a 4 take lambda. That deals with that bracket. And then we've got minus, and in here you've got a 3 take lambda. And here, what we got? Minus 3 plus lambda. You have to solve that. Boo. If you want your calculator to do it, you still got to multiply it out, haven't you? So what does that multiply out to be? If you use, do you know binomial? Yeah, you know binomial expansion, don't you? So I'll use binomial expansion on that. So the what's it rule is a 1, 3, 3, 1. That's the line, isn't it? So we'll have 4 to the power 3 because it's a 9 as the alternate sign. So minus 4 squared lambda, but we've got 3 lots of them. And then we'll have plus 3 lots times 4 lambda squared, and then we'll have minus lambda to the power 3. That should bingo it. Then we've got these things, right? We've got these 3 other businesses. Oh, mental maths. A bit of mental maths for a Sunday afternoon for me. Minus 4 minus 3, it's minus 7. Minus 7 minus 10. And the lambdas, we've got a lambda, we've got 2 lambdas, and I've got 3 lambdas. Right, sorting that out then. We've got a negative lambda squared. Oh, it's going to be like them, but sorry, lambda cubed. What am I about? Squareds, we've got 12. Now lambdas, a bit more of them going on. 3 times 4 squared. 48 minus 48 and plus 3 from over there. So that's minus 45. Then our constant 4 to the power 3 is 64. 64 take 10 is 54. Now I would use my calculator at this point, put it in equations mode. Polynomial, degree 3, and put them in minus 1, 12, minus 45, and pray it gives whole numbers. Solve it, and it says we've got lambda is 6 and lambda is 3 twice. There we are. So I use solve that one, and it gives that straight away. Right, so we've got 3 eigenvalues, 2 of which are the same, and we've got to find now the eigenvectors that correspond to them. So off we go. Let's do it for the 6 first. It's not repeated. So going back to that idea, it's matrix M or matrix A, V equals lambda V. We've just found lambda to be 6, that's the eigenvalue, and now we're interested in the eigenvector. Remember what eigenvectors do? They don't change under the transformation, or they become a multiple of themselves. So the multiple of itself is 6, so that's why we've got that there. Right, expand each row. So the top row's been done for me. The second row now, x plus 4y plus z equals 6y, and then we've got x plus y plus 4z equals 6z. Right, fun now is to solve those simultaneous equations. You might want to write them all equal to 0. So with the first one we've got minus 2x plus y plus z equals 0. We've now got x minus 2y plus z equals 0. So we've got x plus y minus 2z equals 0. You could try if you wish, put those in equations mode. Let's see what happens in the calculator. So equations mode, oh dear, it's having a tantrum. It's a simultaneous, no it's not, get off. It's a simultaneous, it's got 3 unknowns. Put in what we've got there, I wonder what will happen. Naught as the constant. And then 1 minus 2, 1, 0 is the constant, and then 1, 1, minus 2, 0. You mean there's an error? Alright, we're not going to solve it because it says there's an error. Oh dear. Well, to do it by hand, we try to eliminate one of the letters. So we'll try and eliminate, I think we'll try and eliminate Z. Right, if we do, we'll put a 1, 2, 3 on those there. Try and eliminate Z, we just need to do equation 2, take equation 1, yeah? We'll do it the way around. Let's do equation 1, take away equation 2, do the same thing. So that we get is minus 3x plus 3y equals 0. And that implies that x equals y. Eliminating Z for another couple of equations. So this time we'll do, let's do 1 take 3. You could have done 3 take 1, it really doesn't matter. 1 take 3 minus 3x plus 3. Didn't eliminate the Z this time. 3Z equals 0. And this implies that x equals Z. If x equals Z, x equals y, then x equals y equals Z, isn't it? So what we can take from that is that x plus y equals, sorry, that's not plus, is it? It's equals. X equals y and equals Z. So if we make something up, if we take x to equal 1, for instance, it can be found by multiple, the eigenvector can be a multiple of 1, 1, 1, or 2, 2, 2, or 3, 3, 3, whichever floats your boat. So we found eigenvalue for lambda is 6. Now what's the problem with lambda's 3? Let's see. So if we multiply this one out, we'll get okay. Now we try and solve those. We take them over. We've got the last one. It's no big surprise. It's the same thing. Right. What we can get from that is that x plus y plus z is always 0. So we need all x plus y plus z is equal 0. Pretty much obvious, and we read it 3 times, like doing lines at school. Let's do 1, equation 2, equation 3, that. Label those as well. Makes sense then. Or not. Right, so x plus y plus z has got to be 0. So you can make up these really. 2 independent, they're going to be independent value eigenvectors should be, if you want to add up to make 0, we could have 1 as 1, 1 as minus 1, and the other one as 1. Will it work that way? No, it might be a 2. One needs to be a 2. That 2. Let me look professional, I'll do it with that. Right. Okay. And it says, 2 independent eigenvalues. So you've got to think of something else. which isn't a multiple of that one. It'd be independent if that was just 4 minus 2, 4, sorry. 4 minus 2, 4 would also be just not independent of the last present eigenvector. So it's not allowed to be a multiple of an eigenvector we've got. So something a little different. So you can make it up. So you can think about it. If we add 2 as our x, pick any number. No, we'll have 2. We'll have 2 again. But pick 2 numbers that cancel each other out. So we could have minus 5 and 5, couldn't we? That would work, isn't it? Oh, it's a multiple. It's a multiple of that, so it's not right. So that's a multiple of that. So yes, it is 2 eigenvalues, but it's not. They're not. Can I say it? They're not independent. So rub it out. I don't believe us rabbiting on about independence and then just didn't do it. So you might have. Creaky chair. Something like 2. You just have 2, 3. And minus 5, and that comes to 0 as well. Interesting. Okay, other issues. So in finding a final eigenvector, you might have wondered whether your choice of x might fail. The answer is yes. Sometimes you can get equations with no solutions, and in this case you need to look for another possible value. Sometimes you'll find that some values are constrained and only some are free to choose. Oh, right, let's see. So we've got this matrix here, and we're told to find the eigenvector with associated eigenvalue 1. So we don't need to do characteristic because we're told one of the eigenvalues is 1. So what do we normally have? We normally have mv equals lambda v. So really we're getting mv equals 1v because that's isn't it? So mv v, we don't know what it is, do we? X, y, z equals x, y, z. Right, so that equation there, that'll give us 2x plus 2z equals x, y equals y, and 2x minus z equals z. Right, yeah. So if we bring those over, we'll have, if you come to naught, you're going to have x plus 2z equals 0. You have y, naught equals naught. Oh, so naught equals naught, basically, on the middle one. And the bottom one is 2x minus 2z equals 0. Right, that's going to be a little problem, isn't it? I think we can see that. If we try and use 1 to sub in 2, or you could do just solving those equations basically. Let's call them 1, 2, and 3. I can't really call that an equation, can we? 2 and 3. We try and eliminate something now. So if I do equation 1, add equation 3, I'm going to get 3x, and those cancel each other out, equals 0. So therefore x equals 0. Oh. Now if x equals 0, using equation 1, we get 0 plus 2z equals 0, therefore z equals 0 as well. So x equals 0 and z equals 0, but we're not told anything about y, so we can just choose what the heck we like for y. Let's call it 1, be imaginative. Okay, so basically solving those, there's no constraint. You know that x equals 0 and z equals 0. There's no constraint on y, so we choose y to be what we want. I've chosen 1. So an eigenvector is 0, 1, 0. Oh, nice. Right, I think there's an exercise for you to do now. So there it is. Do all the even numbers in exercise 6E. That should keep you off the streets for a while. Having a quick look at that one. Yeah, you'll have fun there. Enjoy. Ooh, before you go, there's this little treat here for you. There'll be a match-up activity on the homework optionals, and this is it basically. You can cut the cards out and try and match the matrix with its characteristic equation, its eigenvalue, eigenvector, and invariant line. And here's the answers to them. If you want to have a go and check, that's lovely. So go out there and have some fun. Right, and I'll see you for matrices 7 later on. Okay, bye-bye.